of class. Okay, so yeah, last time we kind of stopped around here. We found this, this is called Ohm's law, where sigma is this value, n e squared tau over m. That is a result from the Drude model, where we consider like an electron gas under the influence of an electric field. And this formula, n is the number density of charged particles that are moving around. E is the charge of the particles, so in this case electrons. Tau is the mean, the average time between collisions. And m is the mass of the charged particles, which would be, in this case, electrons. So yeah, generally, for this, we're always going to be talking about electrons here. Or more specifically, conducting electrons, because this n is the number density of conducting electrons, not the number of electrons, because most of them are bound to the atom. And then we got, from that Ohm's law, where the current density is proportional to the electric field. That was Ohm's law. If you've ever taken physics before, you may have seen Ohm's law written like this. And these two are related to each other. We're going to see that in our next video. We're going to talk about resistance. So we'll get to this form later. But for now, I want to do a problem involving this electron gas, where we're going to find the actual number, like the mean free time between collisions, and lambda is the mean path. So how far on average is an electron going to travel before it collides with an atom? And so in the problem, we're given the average velocity of the electrons as 1.6 times 10 to the 6 meters per second. Now again, that is the average velocity, which is relevant in this case. We also have a drift velocity, but that's just the change in velocity due to the electric field, which is the drift velocity is very small, where this number is extremely large. But again, these are how fast regardless of an electric field or not, it doesn't change. It doesn't have a significant numerical effect. And so this is how fast the electron's going to travel. This is what we're going to use to see how far it travels before its next collision. Now, for copper, we need the number density, which we actually calculated in a previous video. So I just kind of wrote that result down. We're also going to need sigma, which I looked up in a table. Now, your book will have a table. Well, if you look for it, you're not going to actually find sigma. But later on, we're going to see that sigma is related to another variable called rho, which there is a table for. And so yeah, I just looked it up on a different table, converted it to sigma. And so let's do this problem. Now, the problem is kind of trivial, except for getting the units to work out. So the problem itself is trivial, but we're doing it to just see what results are. This is for copper under typical conditions. We can see how long it'll take for an electron to collide with something, and how far it's going to travel before doing so. So let's do this. So again, first we're going to solve for the mean free path. So let's write that equation here. Let's solve for tau. So that's going to be sigma times the mass of the electron divided by n e squared. Now I'm going to have to write small, I think, because we're going to, you can see the units here kind of look crazy. And I had to write the units in terms of things we're already familiar with. Later on, there's a much more compact way to write this. For now, we've got this mess to deal with. So let's write down sigma Okay, so that's sigma. Mass of an electron is about 9.11 times 10 to the minus 31 kilograms. So we put the 10 to the 31 in the bottom. And we divide by n. Yeah, so over centimeters cubed, so we have to put that on top. And then E is 1.6 times 10 to the minus 19 coulomb. So we square that. Okay, now this is a time. We should get seconds out of this. These are all basic SI units. So we're supposed to get seconds here. So let's see how we can do this. First, let's get rid of centimeters. So 1 meter is 100 centimeters. Let's cube that. And a Newton times, no, we don't want to go that way. Oh yeah, we have coulomb squared here, coulomb squared there. So let's just get rid of this Newton. A Newton is a kilogram meter per second squared. So let's check the units and just see if this gives us seconds. So we have coulomb squared, centimeters cubed, oh wait, coulomb squared times kilograms times centimeters cubed. Now we have meters cubed. I'm going to write that as a meter times a meter squared. And then a Newton and a second squared. I'm going to write it as second times a second. So that is what we have. Oh. Yeah, so sigma, the bottom, we had Newton meter squared times second. I forgot to write that initially. So there it is. So let's look at the bottom now. We have Newton meters squared times a second. Over here we have coulomb squared, centimeters cubed, and then a kilogram and a meter, and that's it. So all that cancels out. We're left with a second. So that's good. So let's clean this up then. So we have 5.92 times 9.11 times 10 to the 45th power, I believe. Let me double check that. So here, 10 to the 19 squared, that's 10 to the 38. And then 10 to the 7, that'd be 10 to the 45. Now on the bottom, we have 8.49. 1.6 squared. Yeah, it's 2.56. And so we've got that, and then times 10. Let's see. Oh wow, we have a big number here. We have 31 and 22. So 31, 53 plus 6. So 10 to the 59. So that's a rather large. Okay. So let's looks like it's in scientific notation here. So let's just look at yeah, this is gonna be around 55 or something divided by about 20. So we should get scientific notation. So I'm going to do 5.92 times 9.11, and then divide by 8.49 times 2.56, being careful to do the order of operations right. So I'm getting 2.48. And then 10 to the 45 divided by 10 to the 59 is 10 to the minus 14. And so this is an extremely short period of time. And let's write that down. So a very short time here. And probably makes sense. I mean, we're moving, let's see, like 1/200th of the speed of light. This is extremely fast. And we're moving in a conductor where the atoms are, the distance between the atoms is very small. So you shouldn't expect it to travel very far before hitting something. And at this speed, yeah, it's going to be a very short period of time. Okay, so that's how long, on average, it's going to take before it collides with an atom. Now what we want to do is find the mean path, like how far does it travel. So lambda would just be this average velocity, 1.6 times 10 to the 6 meters per second, times the average time, which is 2.48 times 10 to the minus 14 seconds. So we'll get the distance in meters, but this is kind of ridiculous. Now we're going to get a very small number. Let's convert to nanometers. That'll probably be more reasonable. So here we have 1.6 times 2.48. So I'm getting 3.97. So just with the numbers, and then we have 10 to the 15 divided by 10 to the 14. So 39.7 nanometers. We cross out the meters and the seconds. So about 40 nanometers before it hits the next atom. Now, the distance between atoms, just look this up. Yeah, the distance it travels is about 150 times the distance between the neighboring ions in a copper lattice. So if we divide this by 150, 40 nanometers divided by 150, 4 over 15, let's see, it's about around 0.27 nanometers. So like the distance between two atoms in the lattice, and let's say around 0.27 nanometers. And yeah, it's going to travel 40 nanometers before hitting something on the average. So the atoms are kind of small. And again, this is still a rather primitive model, not entirely accurate, because this is pre-quantum mechanics, but that's what we're doing in this class. And it's much more complicated if we look at what's actually going on inside a metal, and it depends on the temperature, and also some precise details about the metal. Like if you have a perfect lattice, there'd be no collisions. The electron would just travel and never lose energy. So just travel completely freely. And yeah, we don't really get into the quantum mechanics of it in this class. So the Drude model is the best we can do here. And it's kind of reasonable. But kind of an instructive problem just to get some idea of like how fast these things are moving. 10 to the minus 14th power seconds, that's an extremely short period of time. So, yeah, lots of collisions with the atoms in this model. Okay, so we'll leave it here, and next we'll talk about resistance.